We did k-means clustering, and now we'll look at another way of doing clusters, and that is hierarchical clustering. So with hierarchical clustering, what we have is, we will make, just like we were talking before the break, we will make hierarchies. So saying, you will have, let me delete this guy. So let's say I will have a cluster, and so on. I will have a number of small clusters. I will say these two, they belong to a bigger cluster. Or another way of representing it here would be, I say these two belong to this bigger cluster, and these two belong to this bigger cluster. And I say everybody belongs to, oops. Everybody belongs to this even bigger cluster. So it's a hierarchy. Smaller ones, they belong to a bigger one, and then they belong to a bigger one. So I want to figure out what is the hierarchy in the network. Who are the smallest ones and who are the biggest ones. So in order to do this, the algorithm is fairly simple. You can go two ways. I will start bottom up. Okay? In the bottom up approach, what it says, you start by assigning every item to a cluster. So everybody belongs to their own cluster. So if you have n nodes or n inputs, there are n clusters to start with. Every data point is a cluster of its own. So that's my start. And you have to define some kind of a distance measure and so on. And what we will now do is, we will find the closest pair of clusters. So now what has happened? Let's do this diagram. So these were my nodes, let's say. I'm just doing it in one dimension. You can imagine this is in two dimensions and so on. So what I will do is, I will first figure out the closest pair of clusters. So how do I figure out the closest pair of clusters? So these x's, these are my initial points, and the first step said everybody is a cluster. So every single one is a cluster now. So you are a cluster, you are a cluster, you are a cluster. Everybody is a cluster. Now the next step is, find the closest pair of clusters. How do I find the closest? Some kind of distance measure. Here, this is the distance between these two clusters. This is the distance between these two clusters. This is the distance between these two. So for the first cluster, I have evaluated the distance to everybody else. I'll do it the same for the second one. For the second one, this is the distance, this is the distance, this is the distance, and so on. So for every cluster, I figure out the distance to every other cluster. So now, which is the closest one? So how many I have? N into n minus 1 over 2, right? These many distances I have. Which is the smallest distance? Is this the smallest? Is this the smallest? In this example, this is the smallest distance between any two pairs of clusters. So the next step will say, these two become one group. So now I have n minus 1 clusters. Once this is done, now I have n minus 1 clusters. Now, I have to find what is the center of this cluster. Maybe the center is here. Now I repeat the same thing. What is the distance between clusters? So for every pair of clusters that I have, I figure out the distance. Not just between this and this, but everybody else. every cluster I figure out the distance. Which is the smallest? Let's say these two are the closest ones. So now, these two will become their own cluster. So I'm grouping together. And essentially I keep repeating this loop till everybody becomes one single cluster. So now I have this many. I figure out this guy's center now. And maybe next time, these three are the closest ones. And maybe next time, I don't know, let's say these four are the closest ones. And maybe next time, these two make a cluster. Maybe after that, these guys become one cluster, and so on. So the thing is fairly simple. Every node starts as its own cluster. Then you find the distance between all pairs of clusters. Whichever two clusters are the closest together, group them together. Now you repeat the thing again. For every pair of clusters, figure out the distance. Group the closest ones together. So this is one way of showing the same thing. Let's say I have 5 nodes. In the first step, A and B are the closest, so they get to be grouped. They get grouped together into one cluster. So I'm going like this. Look at the, and in step 2, maybe D and E are the closest, so they get together. Step 4, C, D, and E are the closest, so they get together. And in the last step, of course, there are only 2 clusters left here, so they will be joined together. This is agglomerative, in the sense you start with everybody is separate, and then you group them together. There is another way, divisive, where you start with everybody in one group, and then you try to divide them. And there are the Agnes is an algorithm, agglomerative algorithm, and this is a divisive algorithm. So you can go both ways. Okay. Another way of representing the same thing that I had shown you, I grouped these two together, and so on, is a diagram like this, which is called a dendrogram. In this case, it shows I start with these two together, then I group these two, then I group these three, and so on. This is the whole hierarchy. Let's say I don't care about the whole hierarchy, I just want to figure out who belongs together. Who are the nodes that belong to a particular cluster. What I can do is, when I have a diagram like this, let's say you can tell me how many clusters do you want. Let's say you want 3 clusters. So what I do is I go in the figure, 1, 2, 3, I chop off here. Okay, on top. So I will get one cluster in which there is this guy, these two. In another cluster there is just this guy. And in another cluster there are these 3 together. Right? I have my laptop today, so I can do things like that. Right. Let's say I want to have 3 clusters. So what I do is I chop off here. 1, 2, 3 steps. After 3 steps I chop off my diagram. I don't care about the top part. So one cluster is this, so these 2 together. Another cluster just has these, and the third cluster has all of them together. So these are my 3 clusters. Okay. If you wanted just 2 clusters, and so on, you can figure out how many clusters you want. So let's take an example of how this thing works with an animation. Hopefully that will work. So this is my, this is my initial data. I'm calculating the distance from everybody. So whenever the closest 2, I'm just grouping them together. So this is the closest. So these 2 are the closest. These 2 are the closest. These 2 are the closest, and so on. Every time I For every cluster, I figure out who's the closest. And you see, whenever two nodes are joined, the new cluster, the distance is updated. Its center point is taken. Right? In the end, I will be just left with one cluster. And depending upon how many clusters you need, you can chop off appropriately. And that will give you how many clusters are there. Okay, so it's playing again. So, any questions on hierarchical clustering?
So we cannot limit the number of clusters in this?
No, it will give you all the way from clusters of size 1 to clusters of size n. That's what, and then you can, yeah, you cannot say that I want a cluster of just 5. That you cannot.
Will it not work top-down way? Like
it could work top-down too. So there is this algorithm called GIAN, which will start.
Yes, I can say that I want 5 clusters.
You could get one cluster with 5. Right? So the way this works is, so I have started with everybody in my cluster. Next step, n minus 1 will be in one cluster, 1 will be on another cluster. Right? So I split like that, one at a time, one at a time. Right? So this is what happened in the other way. So let's say I start with A, B, C, D, E. These are my 5, so they're all in one cluster. What I will do is I have to figure out some way in which now, let's say A, B, D and E are in one cluster and C goes in another cluster. In the next step, I will again pick one to be kicked out.
So it will not work like this story figure like from ABCD we are generating AB and CD kind of thing, right?
No, you go one by one. You go one by one, and this time maybe, so C stays at C, I guess, and then you say, you know, A, B and E are here, and D is here. Or it could potentially be, actually, so now I get what your point is, right? So, yeah, but in general it will go like this, one at a time. But that doesn't stop you from developing your own algorithm. You could come up with a way that says, and I'm sure there are algorithms like this, which will say, I will now have 2 clusters here. It could be that A, B and C are here, and what is that? D and E are here. You could develop an algorithm like that. It's not a problem. You just have to define the distances appropriately and then do it. Alright. So what are the problems? One of the things is the complexity. Order of n squared. Why? Because when you are doing the distance calculation, right? How many distances do they have to calculate? Between every cluster. So n into n minus 1 over 2, that many distances. So that's n squared, order of n squared. So it's fairly complex. And whatever you have done is done. If you have joined these two together, you have joined them together. You're not going to come back and separate them later. If you looked at k-means, which cluster you are part of right now can change. Maybe I belong to cluster 1 right now. But after the new centroids are calculated, it is possible that I can move to cluster 2. So things can change. Here, no. If I have joined them together, I have joined them together, that's it. Sometimes that can be a problem. Then there are things like, there's a hierarchy, right? And so there is nothing distinct which says, this is different, these groups are different, and then, so there are other issues. So that's fine. You don't need to spend more time on this. So now we'll come to the last part, which is principal component analysis. And the main reason for using PCA, as we call it, is really for dimension reduction, dimensionality. If you have data with 50, 60, just for humans, right? If I give you data with 12 different dimensions, you're measuring temperature, pressure, humidity, something, 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 it becomes very difficult for us to visualize what is going on. Right? Let's say I have a machine, and for that machine I'm measuring many, many things. What is the speed at which it is spinning, what is the temperature, this, that, and I want to tell you whether the machine is behaving correctly or not. Then your question would be, I have to look at so many parameters. I don't know. But it may turn out that some things are more important than others. Maybe the rate at which it is spinning, how many revolutions per second or per minute, that's most important. Temperature doesn't really change much. So what we want to figure out here is, which data is the most important? If something doesn't vary at all, if the temperature is always between 29 degrees and 29.2 degrees, that's probably not going to tell you whether the machine is going to fail or not. Right? But if the speed at which it's revolving goes from 50 revolutions per second to 150, that's probably going to tell you something more. Right? So what PCA allows us to do is, it allows us to figure out which is the more important data, the more important dimension I should be looking at. So if a particular data attribute is not important, I just don't care about it. I just throw it out. Which allows us to reduce the number of dimensions we have to worry about. So let's see what's happening. So this is sort of what I was saying. So often we want to understand some phenomena with various quantities. And so much data, they may have noise, I don't know what's going on. But the underlying thing may be actually quite simple. Maybe your machine breaks down if the number of revolutions goes beyond 100. In that case, looking at temperature, pressure, maybe is unimportant, not needed at all. There's a very simple explanation as to why your machine is going to break. But if you have so much data, you don't know that. So I want to figure out what is important. That's the thing. As an example, so now let's come to what is the fundamental principle behind this PCA thing. Right? Let's take an example, right? Try to motivate it. So let's say we want to study the motion of a spring. You want to do a physics problem, I want to study the motion of a spring. And in this case, it's an ideal spring. It's like this. There's a spring and I have a ball attached to it. So if I pull this ball and release it, it should keep going like this, right? And what you can imagine in this case, it's only going to move along the x-axis. There is no horizontal thing, vertical thing, nothing on the sides. It's all along one direction. But let's say we don't know anything about physics. I don't know anything. I have just come in, and this is a standard. So this is a standard of the motion along the x-axis. Right? So now I don't know anything about this problem, but I still want to characterize what's going on. So since I don't know anything about physics, what I say is, all right, fine. I have to observe what is going on. So how am I going to observe it? Let's put 3 cameras here. And these cameras will take a picture many times per second. Right? They will take a picture. So what I will get is a 2D view of what's going on. Right? So I have 3 cameras put in, they're observing things. This is sort of, you can think that you have so many types of data coming in, observing the same thing. Temperature, humidity. So I have all this. But since I don't know much, I can put the cameras randomly. I can look in this direction, I can look in this direction. And the cameras don't necessarily have to be perpendicular to each other. They don't have to be aligned at 90 degrees, right? Which is ideally what I would want. So each one is aligned to a particular axis. But in this case, they're randomly aligned. So what will they observe? They will observe some kind of a projection. If this is here, and I'm looking from the top, I see the projection on my eyes, right? So I don't see that, that's what it is. How many of your engineers and how many of your just computer science were engineers? So did you do like drawing and things in your first year?
Yes.
So then you know what I'm talking about, right? So depending upon which angle I'm looking at, I will see a different projection. I will see something in the x direction, something in the y direction, etc. Since I'm dealing just with 2D here. a camera is taking a 2D picture. So depending upon where I'm aligned, in which direction, maybe the spring is moving like this, but I observe this. And I can break it up in the X and Y components. But the three cameras are aligned in three different directions, so I don't know. So the X and Y axis of the three cameras are not aligned. So now I could make it even complicated. What I'm getting is, let's say they are sending 200 images per second. Right? And we don't even know where the real X, Y, and Z are. And we are just getting some random thing. And what I really want to do is, I know, for example, in this case, everything is really just in the X direction. So now I have, what data do I have? I have camera images from three different cameras. Each one is giving me X, Y, X, Y, X, Y. So I have a 6-dimensional input value now. Right? A camera is giving X1, Y1, X2, Y2, X3, Y3. This has its own orientation, this has its own orientation, this has its own orientation maybe. But if I really had to, since I know here, if I plotted something like this, everything will be along the X direction, let's say. This will say there is variation in this and this. There is variation in this direction, this direction. But if I put everything together somehow, smartly, I will just realize that there's only, effectively there is only variation along a straight line when the spring is moving. And that's really what PCA is trying to do. You give me data from different dimensions, looking at it from different views. I will try to tell you where, in which direction really the things are happening. So that's the idea of PCA. So the goal is, it will compute the most meaningful basis to re-express your knowledge, right? So these are my bases right now, in this, in this, in this direction. I want to somehow twist them or turn them in such a way that the basis functions for each of those dimensions will be in such a way that I will figure out exactly what's happening. I won't have to have 6 different dimensions of the data, only one dimension will be good enough. And hopefully this will filter out the noise and other things and so on. And in the spring example, the goal of PCA is that I have to somehow come down and figure out that all the dynamics that you told me, they're really along the x-axis. Okay? And another way of looking at it is, we have to determine that the basis vector, so how do I move from here to here to something that looks like this? That's what I really want to do. Or to do that, we need a couple of things. We need some information about probability and statistics, and we need some linear algebra. So this is fairly simple. If I give you n pieces of data, you can calculate the mean. Add them up, divide by n, you have it. You can also calculate the sample variance. So here I had 6, right? x1, y1, x2, y2, and so on. So for x1, I can figure out the sample variance by calculating the mean and then taking the difference from the mean, squaring, and dividing by n minus 1. I could also pick x, so this x1 is a little bit different than this x1. And so y1, y11, y12, and so on. And I also have an x2, which corresponds to this. I have a y2, which corresponds to this. Right? This x1 are all the values I'm getting for this guy. Okay? But anyway, so if you have two different vectors, x and y, of values, you can also calculate their covariance. And there's a standard formula for covariance. And the other thing that we will need is linear algebra, and specifically we will need eigenvalues and eigenvectors. So when we did linear algebra in high school or first year math or something like that, we know what's an eigenvector. If you have an n by n matrix A and you take a vector x, if x is such that A times x is the same as lambda times x, where lambda is some scalar, then we say that x is an eigenvector. Right? And this lambda value is what is called an eigenvalue, the scalar by which we multiply the vector. Right? That's eigenvalue. And the way in which we find the eigenvalues is we take the vector A, subtract lambda times the identity matrix, the diagonal one, sorry, the diagonal matrix, multiply by x, and solve for lambda. When A and x are given, you solve for lambda, you can get your eigenvalue. That's fine. But what does it really mean when we do this? What is it doing? What are we doing? So consider any vector. Right? Let's say I have 1 and 3. Let's say x1 is 1, y1 is 3. Right? And take another matrix. Let's say this is my matrix, 2, 3, 2, 1. Let me multiply them. So if I multiply these two, this matrix with this particular vector, this is the answer. So what has happened fundamentally? What have I done? So what is this 1, 3 or 1, 3? It's a vector. If you think of x as 1, this is, if you think of this as x and this as y, 1, 3 is essentially a vector that goes from the origin to 1, 3. That's a vector. What I did is I multiplied this particular vector with a matrix like this. And as a result, I got 11, 5, which is essentially another vector. So in another way of thinking about what's happening is, you think of this matrix as a transformation. It's a transformation, and what it is doing, it took this vector, transformed into this vector. That's what happened. Now in this transformation, two things happened. The direction of the vector changed, the magnitude also changed. So the direction is different now, magnitude is also different. That's what typically happens when you do matrix multiplication. Right? That it transforms the vector, it changes everything. But in some special cases, if you, for example, consider this particular vector, 3, 2, take the same matrix that we have before. So you apply essentially the same transformation on this matrix. You multiply it. You get 12, 8. Which I can write as 4 times 3, 2. So what happened now? I have the same transformation, right? Right. What was it? 3, 2. Let's say this was 3, 2. I do the same transformation on it. And what I get? 12, 8. So I did a transformation, but only the magnitude changed. The direction did not change. Right? And that's the special thing about an eigenvector or an eigenvalue. So this is an eigenvector for this particular matrix. So if you do this transformation on this matrix, you will get along the same direction but not. That's right. And this is what we will be trying to do in principal component analysis. We will try to transform our data along certain vectors, along certain directions. Right? You can think of this as your data, and you will multiply it with something that will transform along a certain direction. And this is not the only eigenvector which is possible. Right? There could be another vector which will transform it, but that transformation will be maybe in this direction. So 3, 2 is not the only one which is possible. There can be another one. If you multiply, you will also get things like this, same direction, different magnitudes. But what you will find is that particular vector and this 3, 2, they will be orthogonal to each other. So the eigenvectors will be orthogonal. They will be at 90 degrees here, essentially. So these are properties of eigenvalues, eigenvectors, and so on. Right, so this is, so essentially what happened is eigenvectors, they do a transformation, but it's reflected. It's along the same line as before. And there are some specific properties, you can only find them for square matrices, but not all square matrices have eigenvalues and eigenvectors. There's some special things that you need to have. And if a matrix does have an eigenvector, there will be an n of them. In an n by n matrix, if it has eigenvector, you will have n of those. And this will only change the magnitude but not the direction. And all the eigenvectors will be perpendicular or orthogonal to each other, no matter how. Even if you have n of them, right? You have n, all the n will be mutually orthogonal. So in this example, there is 2-dimensional, and so on. So these are fine. And so this is probably not very important to us, but when you have an eigenvector, mathematicians would usually represent it in unit language. That's fine, doesn't matter. So in this case, whatever it is, so we have talked about all of this. Okay. So now let's see what I want to do in PCA. In PCA, what I have is, I have a data with many variables. I have p variables. In this case, I had deleted it, but I had 6 variables. From the 3 cameras, each one was giving x and y, x and y, x and y, 6 variables. And from that 6 variables, I want to come up with a smaller set. Maybe just one in my camera, in my spring example. In real life cases, maybe you have 6, you want to come down to 4 or 3 or 2, whatever it is. You want to do that. So this is the idea. You have this matrix A. It has p variables and you have n of them. And from here you want to come to something which has just k variables. So each input data that you have, I will go from p dimensions to k dimensions and reduce it. So that's what I want to do. And how do I do this? The way I will do it is, I will take the data that I had from here and I will summarize it. So I have data all over. Let's say I have both positive and negative data. And this was my original axis, the usual x and y. Essentially what I'm trying to do is, I'm going to try and find projections along these axes. Earlier, what was the value for this particular data point? X, y, right? That was the data value earlier. Now what I do is, I find these new axes and I do the projection. And say for this particular point, this is the new x, and where did it go? This is the new y. So I change the way in which I look at things. I don't look at the original x and y anymore. I twist my axis a little bit. And the trick is, in which direction should I twist? Should I twist my axis a little bit, or more, or more, or more? And that's what PCA will try to do. And the idea is, I will twist my direction in such a way, along the axis where the variation is the highest of the data. If the data varies a lot like this, I will twist there. If the data varies a lot along like this, I will twist there. That's really what PCA is trying to do. And after twisting, if I see, most of the data, see earlier the variation was like this. When I twist, everything probably is like along this line. So this dimension is not important anymore. I can get rid of that dimension. I will show you this in pictures later, so hopefully it will be much easier. How are we doing? What is the time? Oh, we are doing quite well today actually somehow. But yeah. Right. So, hopefully, since I have gone from P to K, I am losing some information now. If I keep this, I had 2 initial ones and I have 2 now, everything is fine, I don't lose any information. But if I say, I will only look at the X component now, I don't want to worry about the Y component, I will lose some information. but hopefully not much. That's the whole idea about PCA. The first K components that I choose, they will show most of the variation in the data, most of the interesting stuff in the data. And whatever I'm throwing away, they don't have much. It's like only a variation of 0.01 or 0.1, so it doesn't make much of a difference. The data is more or less constant along those lines. So this is the algorithm, or the steps that you want in order to do principal component analysis. First step, you get the data first. Right? That's, in our case, we'll get the camera data. So we'll get the data, everything is good. Next step, subtract the mean out from every data value. So if you have, so in this case, I have X and Y. I calculate the mean along X, I calculate the mean along Y, X values and Y values, and then I subtract them. So after step 2, what I have is, I have the original data, but the means have been subtracted out. So this is what is called centered data. Our data centering. I'm centering the data, so I've subtracted the means out. So now if I take the new means, it's 0 everywhere. All right. Next step. So we had this, right? So this is what is happening. We had X and Y. So we had this data. I calculated X bar, Y bar. I calculated the mean. Now I got new data. X prime, Y prime. What is Y prime? Original Y minus Y bar. And this is original X minus X bar. So I have the data now. What is the mean? 0. This is what I have now. On this data, this guy, I will calculate the covariance matrix. So what will the covariance matrix look like here? It will be a 2 by 2 matrix because I have 2 variables, right? So I will have it. I will have a 2 by 2 matrix like this. These will be the variances, and these will be the correlations. It will be a symmetric matrix along the diagonal. Right? Anyway, fine. So now I have the covariance matrix. Within the, now for this particular matrix, I will calculate the eigenvectors and the eigenvalues. So I calculate the eigenvectors and eigenvalues of this covariance matrix. So hopefully I get 2 eigenvectors and 2 eigenvalues. Fine. And now, so I have 2 eigenvectors and 2 eigenvalues. I will order them. I will order the eigenvectors by their eigenvalue. In this case, I will have 2. One higher, one lower. Now you can pick how many dimensions you want. In this case, I have just 2 options. But I have 3 options. I can keep both dimensions. Or I can pick the one that I think is the most interesting. Or, which doesn't make sense, is to say I don't want anything. 0. This is a simple example where you just, at most you can reduce by a dimension of 1. But if you had x1, x2, x3, x4, x5 and so on, let's say 500 dimensions, you can choose of those 500 original dimensions of your data. Do you want 300 to remain? Do you want just 5 to remain? So it's much more interesting, right? So anyway, so you've calculated the eigenvalues and eigenvectors, order them. Order them according to the eigenvalue. And whatever dimensions now you want to live with, pick the top k. Let's say you want k dimensions, up to this p, I guess. You pick the top k. And this becomes your feature vector. The top k dimensions you want to look at. And now you want to do a transformation of your data, and that you will just do. You take this feature vector, you make a transpose of it, multiply with the centered data. So what will happen at this point? Every centered data, just like I was figuring out these projections, you will find out the projection along those axes. That's what's going to happen. So this is fairly simple, right? But now let's try and visualize it. So algorithms are something that usually, at least for me, if I visualize it and see what's going on, then I have a better understanding of what's going on, right? So let's try that. So before going that, so why am I doing all of this, right? So I already did that here actually. So there's a geometric rationale for this, right? So the variances and covariances mean certain things, right? Variances means how much you deviate from your mean, and covariances tell us how x and y are related. If the covariance is large and positive, that means sort of a linear relationship between x and y. If x increases, y also increases. If this is large and negative, that means they're negatively related. If I decrease, you increase. And if this is around 0, that means no relation. I can't really say. I can increase, you can decrease. Sometimes I increase, you also increase. No relation. So this is what covariance says. Now here, what is happening? This was 2 dimension. So I could see how they're distributed. In 3 dimension, you can imagine your data point to form a cloud of some kind. That's how you distribute. And you can go in higher dimensions and so on. And the objective of PCA really is to rotate the axis, just as I was rotating like this. So that so you figure out along which direction most of the variance is. Right? Let's look at what is happening using a diagram. So let's say this is my data. I have 2. Well, I guess I'm saying x1 and x2, but two pieces of data along 2 dimensions. My data has 2 dimensions, and this is what the data looks like. Right? I really cannot say which is important and which is not very important here right now. It looks like it's spread out. Though there is something like this, but it's fairly spread out. Can't really say much at this point. So what is the first step of my algorithm? Subtract the means out. Right? So I will calculate mean of x2, mean of x1, and subtract that out. So the mean of x1 is 8.35, mean of x2 is 4.91, and the variances are like this. Okay. Now I can subtract it out. Now once I subtract out from the covariance and correlation matrix, I can figure out what the eigenvectors and eigenvalues are. And those will be my important axes. So this is one direction of the eigenvector, and this is another direction of the eigenvector. And if you look at this, what it says is most of the data varies along this line. Rather than looking here, if you look in this direction, you will see the maximum variation. If you look along this direction, what is the variation you will see? You can do it intuitively. Somewhere between here and here. And if you look along the traditional x direction, you can see the maximum variation is this, right? This is the lowest data point. This is the highest data point. So this is the variation I see. But now if I change my way of looking at the data, I look and say this is my x-axis. What you will see is, this is, I guess, the lowest point here. This is the projection here. And this is the projection. So now, my spread is this much, which hopefully is larger than this. So now I have figured out which way to look at the data. That's really what PCA is doing. So let's look at the steps and see what's going on. So what I'm really trying to do is, I'm doing a rotation of the original variables. And let's see what's going on. So, the first step was to center the data by subtracting the mean out. Then I said, figure out what is the covariance and the variances. So, This is what is called the variance covariance matrix over here. And the diagonals and the variances, so this is the variance of x, this is the variance of y, and this is the covariance between, well, this is the variance of x1, this is the variance of x2, and these are the covariances. And what this really tells you is, this is higher, right? So what did we do next? We look at the sum of the diagonals. So this is giving you some intuition about how to interpret the data, right? So this is the sum of the diagonals, which is these two, and there's a special name for it. It's called the trace. This sort of gives you some idea about what is the maximum variation you can expect in the data. Right, so this is the trace, and this represents the total variation in the data. Right, and then these things, if you want, you can imagine, but otherwise it's fine. Next step, we find what are the eigenvalues and the eigenvectors. So I take something like this. S is my this is the S matrix, 2 by 2 S matrix, and then usual way I find what is the eigenvalues and the eigenvectors. And in this case, I will just get a 2 by 2. Right? And in this case, these are my two eigenvalues, 9.8, 3.2. And just by looking at this, I can say this is much more important than this one. And if you look at this, if you add these two up, you will get your trace value back. And using this, I can also figure out what my eigenvectors are. So when I solve this, from eigenvalues, these are my two eigenvectors. This is eigenvector 1, this is eigenvector 2. And again, these are orthogonal. If you multiply them, they will come out to be 0. That I can verify. And this is this vector, right? This is one vector. And if I go back to my figure here, this is that vector. This is that vector. And the other vector, eigenvector that I had, this is the second eigenvector. So all of this is fine, but let's take an example of how we can do our dimensionality reduction then. So this is what I have. Let's say this is another example of x1 and x2. This is my original data, x1 and x2. First step, calculate the means. Subtract out the mean. So this is my center data. So this was the original data. When I center it, this is what it looks like. So I've subtracted the means out. So every point in here, I've subtracted the x mean and y mean. So this is what it looks like. Now, I calculate the covariance matrix. So this is what it looks like. Solve this for eigenvalues and eigenvectors. These are the eigenvectors, these are the eigenvalues. And in the previous example that we looked at, one was 9, one was 3. One was higher but still comparable, 3 and 9. In this case, there's a 10 times difference. What that tells you is, along one axis, there is 10 times more variation than the other one. Right? So now, what I can do is, the second eigenvector is more important. So maybe if I want to do dimension reduction, I don't need to worry about this at all. What I will do is, I will take this eigenvector and multiply each one of these, x1, y1, x2, and get the projection along direction x2. And this is what it will look like. Now, if you just care about that particular direction, this is what your data is. So from 2 dimensions, you have converted the data to a single dimension. And you can apply it to much more general cases. Questions? All right. So, anything related to the course? Today I finished early. I don't know what I did today. Maybe I went too fast or something. Half an hour early. How many of you have signed up for the exam tomorrow? No one? Oh, come on. I was hoping you'll go home and whatever, have some fun in the city, so I have to make a question paper.
Anything on the enforcement learning that is
Reinforcement learning? So the reinforcement learning, I would say the most common one people would use is something called a Markov decision process. In this case, what happens is, I say, okay, I first have to define states of my system. Okay? Let's take a concrete example about something, right? And since we are doing IoT, let's talk about sensors. Okay? And the example I'm going to take is, let's say I have a sensor here. This is my sensor. Okay? And it doesn't have a battery in it. Instead, what it does is, this is a fairly, one of the, I guess, was quite pop. I guess started about 10 years ago maybe, and now it's increased more in popularity. So this sensor doesn't have a battery, but it's based on energy harvesting. How do you harvest the energy? 10 years ago, people would say put a solar panel on it. Now people would say, just put your sensor here. This is my sensor. There is Wi-Fi or TV or cellular radio going around. Just catch that signal and put it through a rectifier or something and store it in a battery. And battery these days is a capacitor. It stores it in a capacitor. That's what it does. Fine. So it's doing energy harvesting, right? And what I will do then is, it has a battery. The battery looks something like this. It has a maximum limit you can go maybe. How do you harvest the energy? This is a random process. Right? I don't know how much energy will come. Maybe it's cloudy. Let's just say solar. Maybe it's cloudy, so I don't harvest much. Maybe it's sunny, so I harvest something. And what I'm going to do is I'm going to look at it usually in discrete time intervals. I look at the first time interval, second time interval, third time interval, and so on. And I say, okay, what is the probability or what is the distribution that tells me how much energy I'm going to harvest? Some distribution. And now, let's say I have data to send. I have data to send. Again, I may have data to send, I may not have data to send. That's also random. If I send something interesting, I will send data. If I don't, I will not. Or it could be that every second I generate a data, so I will send anyway. So it depends on what your scenario is. But now let's say on the sending side, I have two options. I can either send at high power, or I can send at low power. If I send at high power, I will drain my battery faster. So what can happen? Maybe later on, a data packet comes in, I have to transmit it, there is nothing. I may get into trouble. If I transmit at low power, then I don't spend so much energy. So hopefully, cannot guarantee it, but hopefully if a packet comes in later, I still have some battery power left, right? It's more likely that I will have something in my battery left. So I would prefer this. But if I transmit at low power, it's more likely that I will have errors. My receiver will not be able to decode it. Depends on the signal to noise ratio, right? This means your signal to noise ratio will be lower because your signal power is low. So error is high. Error is low. So now you may have to come up with a machine or some kind of a decision process that says, I give you the battery level, current battery level. I give you this distribution. Data packet has come in. What should I be doing? This or this? So that's something I need to learn, or I need to make a decision on. So in this case, the first step is you define your states. What's your state? Could be a single variable, could be multiple variables, could be whatever. What would be my state here? So as the designer, you have to figure it out. In this case, I could say my state is, what is the current battery level, B? That would be my state. Intuitively, you see, if my battery is full, I go for this, right? If my battery is near zero, I go with low power. So battery is important. Essentially by state, you want to figure out those variables that are important for you. So battery is important for me. What else is important? Maybe I want to know if I'm harvesting energy or not. If currently the sun is out, I can use this. If it's nighttime or cloudy, maybe I use this. So maybe, what is the state of the harvesting process? And if you think that this is a random thing, you could add that. If it is not, but let's just say we have these two. This is my state. Now you also say, okay, what I'm trying to do, I'm trying to make a decision. Decision on what? Whether this or this. So that's my action. Action says high or low power. So now your problem is, based on this state, tell me what to do. It is like you're classifying again, if you want to think about it like this, right? So I had a pretty, so one of the first persons who worked on neural networks back in the 60s used to joke with me and say that, Biplab, every problem in life is a pattern recognition, but he was a pattern recognition person. So every problem in life is a classification problem. So this is classification. So if you tell me the state, what should I do, high or low? In order to do that, what I will do is, I will say, okay, what is the cost of doing this action? Or equivalently, what is the reward I get for doing this action? So you have a cost function or a reward function. Same thing. One is the negative of the other maybe. So what is the cost of taking action A? Well, A can be either this or this. So I define that. And finally, let's say so currently my state is something, S1. Right? My battery level is some value, and my sun is out or sun is not out, something like that. There are two H's, so maybe I should change that. Let's say this is the sun. Whether the sun is outside or the sun is not outside. So I was in some state to begin with, let's say. Some value of the battery, some value of sun. Now, if I take a certain action, which state will I land up in? You have to calculate that. You say, for example, let's say the battery was B, and the sun is not there, so it's gone. So I'm not harvesting anything. And action equals, let's say, high. So what will be my next state? Next state will be, battery will be B minus something. If you transmit at high power, you lose this. This is the new battery, right? What will be my sun? It could be still no sun, or maybe the sun has come out. The battery value will not change in one time, right? So battery will be. the sun. This is the new state given this action. But it could be either this or this. So there must be some probability associated with it. What is that probability here? Battery is deterministic. If you transmit a packet at high power, you consume 1 watt or something, 1 ampere hour, whatever it is. So I know exactly what your battery will increase by. But this is random. So now it depends on what model I assumed about the sun to begin with. So this happens with probability, whatever it is, let's say P1, this will happen with 1 minus P1. So now there are probabilities associated. So what I'm doing now is, I have a state transition matrix, and they have probabilities associated with it. So now what Markov decision process will do is, it will figure out what is the optimal action. So it will figure out a cost for every possible action and essentially take the average. And it may also look in the future. If I do this now, what will happen in the next time, next time. And there are standard ways of solving this. Right? So this is one instance of reinforcement learning because I care about the cost or the reward. If I take a certain action, I will get a certain reward back. And I want to take the action which will sort of maximize my reward, either right now or averaging from now till infinity in time. So there are different ways of defining that. This works out fine, but the problem is the state matrix. Usually in a realistic system, you would have many, many states. So this matrix will be very large. So there's a computational complexity associated with that. But Markov decision processes are at least in academia, if you want to write a paper, a good thing. See, somebody said talk about research a little bit, right? So in the end, what turns out is that most people learn some tools, and then they use that tool rest of their life. So whoever is a pattern recognition person, they look at everything as a pattern recognition problem, and then they try to solve it accordingly. If you're an optimization person, you think of every problem as an optimization problem, and then you solve it. So if you're a student here or anywhere, when I was a student, I used to tell my master's advisor, right? So I was in what was called telecommunications, I think my specialization was. But there were just 2 or 3 networks courses, maybe 2 courses. So I used to say, sir, there are no networking courses. And at the time, I was young, I didn't realize things, and he would say, why do you want to do networking courses? You've already done one. You are in college now. Use this to learn as many tools as possible. So you don't want, so that would be my advice to if you're in a master's program or PhD program. If you're in networking or whatever it is, pattern recognition, you don't want to just learn pattern recognition. Learn other things. Learn tools, because those are the ones which will be useful later on. So, if I, for example, my students, I would tell them, go learn about game theory. It may not have anything to do with research. You just don't want to do courses that's on your research. That's a bad idea. Your research, anyway, you're spending 80% of your time on your research, let's say. Assuming you don't have a job, you're not doing part-time PhD and things like that. Anyway, you learn about your domain. Use this time in college to learn other things. Learn optimization, how to do optimization. Learn queuing theory. Learn time series analysis. Later on, if you have these things, you will see that the problem you're trying to help do now can be solved by these techniques. Now, a lot of people do game theory for networks and so on. I can't do it. Why? Because I don't know game theory. If I had done a course in game theory back in the 90s or something, I could have done game theory. And another thing right now is, so this is for the younger people here. Don't think that you will be doing whatever machine learning all your life or computer networks all your life. Things change. I started doing something else. right? And the same problems don't stay. Whatever is, so today, if when they talk about history of machine learning, it started in the 50s, became popular, then died down, then became popular, then died down. Your research career would also be something like this. Whatever is important now may not be the same thing after 5 years. So at that time, you don't need to know what is TCP/IP. You need to know fundamental tools like game theory. I'm just picking on game theory, but your stochastic processes, optimization tools. So that's really what you want to learn. Let's say I started giving you GIAN, right? Philosophical stuff which you probably don't care about, but anyway. By the way, if anybody is looking for a PhD position, my friend wanted me to send something. I don't think he has. I am on the network. Yeah, and so my friend at the University of Central Florida wants PhD students. So if you're looking for a PhD position, write to him. He does, you can look at what he does. But where is his email? Yeah, here. Murad.yuksel@ucf.edu. So in terms, somebody said talk about IoT research, where IoT research is going. To be honest, academics, we do something, and real world and industry will do something else. One of the challenges in the industry right now is standardization, of course, because everybody wants their own protocol and standards. So there's no interoperability now. And the other real challenge for IoT is really that there is no business case yet. We talk about all of these applications, IoT for this, IoT for that, but if we are not going to make money out of it, it's not going to be there. So far people have not figured out how to make money out of it. If I was a telco, then I would say, okay, if I have to support all of these IoT devices, I will only do that if they pay me money. Are people willing to pay money for it right now? Not yet. In terms of networks, common things you will hear these days are energy harvesting, let's say. So this really means you want to minimize the energy consumption. Whatever protocol or other things that you have should minimize the energy consumption. And so that also, not just communications, even when we were talking about all these machine learning things, right? Can a sensor node run a perceptron or a neural network? Probably not. So you have to do something else maybe there. So you want to optimize your algorithms for low power, low complexity devices.
So can we provide some intelligence from the sensor?
Yeah, you can. And then depends on what kind of sensor you have. So a lot of people try to do that, right? So in that case, again, this is a trade-off. What is the accuracy of your whatever you're doing versus the energy cost? If you will give me unlimited resources, I will be fine. But in a real system, I don't have unlimited resources. So what is the best I can learn or decide, but with low complexity? So this Markov decision process that I was talking about, right, MDP. In the end, what does it output? What is the output of MDP? Output of MDP is, if you're in this state, this is the action you need to take. This is the optimal action. Or if you're looking at it from a image processing or any other intelligence kind of thing, it says, if this is the state, then this is the classification. Same thing. Instead of action, I could say, okay, if the state is this, I classify this as male. If the state is this, I classify, the state could be the picture, the pixels of an image. I gave you the example of a sensor, but state could be anything, right? State could be your, for example, you're doing that Boolean function. Your state could be that, and your output could be whatever output it is, right? So that doesn't change. So given a state, I have an action or a classification. Now what I said is, in a real life system, the state becomes very large. When you are talking battery, battery is a state. How many states are there in a battery? A typical battery, so how was my state changing? Every time you transmit a packet, you have to change your battery by, let's say, B of H. So this one, then I will count in terms of the number of packets I can send, total number. What is the battery's capacity? And every time you transmit a packet, you decrement by 1. How many packets can how many packets can you transmit on a given battery? We did some calculations with Bluetooth at some point, right? But this can probably, let's say, send 10 to the power of 6 packets, a typical small cell. That means you have 10 to the power of 6 different inputs here. If you're thinking images, right? Let's say the simple 30 cross 32 images. 30 cross 32 pixel images. So I have 960 pixels. How many different types of images are possible? Depends on what those values are, right? Of the pixels. Let's say pixels are binary, 0 or 1. So each pixel can be a 0 or 1. So 2 to the power of 960. Crazy amount, right? So if you want to classify every image, then you need to have an entry for all of these possible pictures. Not possible. Right? So essentially what we do for MDP and so on, ultimately this is what we are trying to do. This will tell us what the idea is. You try to learn the structure of the problem. When I was doing this battery, right, should I transmit at high power and low power? I will have a table. State 1, state 2, state 3, all the way up to state, let's say, 10 to the power of 6. And for each of this, it will tell me what action I should do. Maybe when this is low battery, this is high battery. So I should do low, 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 and at some point I will do high, 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 high. If the battery is high enough, you just transmit at high power. So you can solve all that fancy problem. Ultimately, the decision is really very simple. It's a threshold. If the battery is lower than this, transmit at low power. If the battery is higher than this threshold, transmit at high power. So all that fancy calculation and math and so on that you did, you can boil it down just to one line of code. If battery greater than this, transmit at high power. If battery lower than this, transmit at low power. That is really what happens in a practical system. I will solve the complicated problem in my computer or whatever, then I'll try to see what the structure looks like. When I'm doing image classification, whatever it is, right? I can say, if most of the pixels on this side are black, I can just classify it as one thing. I don't need 2 to the power of 960 cases. I'll just look at the structure of the optimal solution. And then put a heuristic just to approximate that. And if you want to publish a paper, then you say, okay, this is the optimal thing's performance. This is my heuristics performance. This is the bound. Right? Or this is the performance ratio. Those are paper writing tricks. But in real life, I cannot store even, so this is a table of decisions. If I want to put it on a sensor, I cannot have 10 to the power of 6 lines of table just to store things. I would just rather have a simple solution. And that's what you want to do. All this math and tools and everything is fine. But figure out what's really going on. And in some cases, If you're Google and you're just trying to figure out, or if you're Facebook, you're just trying to figure out if there's an image on a particular post or not, then you don't care. You have lots of computers, build a neural network that will figure out, or a deep learning thing that will figure out if there's an image or not. Right? But from an IoT perspective, where you have resource limitations, maybe you want to go somewhere else. Now we are at 30.
Sir,
Yeah.
research in computer science is driven by industry and not by the people in computer science actually want.
So, depends on where you are. Research in computer science is done by organizations like Google, or these days China spends a lot of money. All this Baidu and what do you call it, Tencent and the 3 big companies in China. They spend a lot of money on computer science research. And then the US, most European Union, US government, even Singapore by its size, they also spend money on computer science research. But the reality is, in the university, the focus is different. Outside the university, the focus is different. In many places, you will see the administration or whoever, they will say, academic university research should be governed by what's happening in the industry. I have never done any research that's related to industry. And to be honest, I will never do it. It's just because, I'm in my own world. I'm happy there. I have a job. That's not going to change. And that's what happens. And then another thing is, the kind of problems that the industry is interested in is very different than the ones I want to solve personally. I want to solve, for example, if I have an algorithm like this, how close does this threshold thing, how close does it come to the real optimal performance? This is an approximation. I want that. I want to spend 2 years or 3 years or 1 year just to come up with an equation for that. In real life, they don't need that equation. Right? They are just happy with this. But that's not what I want to do. Right? And nobody can force me to do it. And unfortunately, that's what happens. And the other thing that changes things is, in university, we are judged by something else. In industry, you are judged by something else. In industry, ultimately, you are judged by whether you are making money or not. Whatever technology you are developing, is it converting to a product which is selling and thus bringing revenue back? For me, at the end of the year, my head of the department or dean doesn't care. He or she cares how many papers I wrote. So again, this is reinforcement. So I get rewards if I write papers. I don't get rewards if I sell whatever, if I get a patent. So then I get pushed towards that thing. In India, systems are different, right? In the US system, what we had is the concept of tenure. So when I joined as an assistant professor, it was for 3 years, 3-year contract. After 3-year contract, if I'm doing reasonably good, they will give me another 3 years. And at the end of 6 years, they will evaluate what have I done on my teaching, what have I done on my research, and so on. If I'm okay, then I have a lifetime job. So then do I care? And then I know when that evaluation time comes, they will be looking at how many papers I wrote, how much funding I got in. Even if I have 500 patents in one paper, I'm not going to get tenure. Right? So what do? I write papers. And that's what has happened actually. And now, for example, academic jobs are becoming more. So when I graduated, we didn't even have journal papers and you could become an assistant professor. Now, can you do that? No. Now I think the government of India says you have to have 2 journal papers per year, right? So that's the minimum. So it's not going to happen. So then if I have a student, what do I tell? I know that student wants a job at the end of it. So we go towards paper publishing. So the system is geared, no matter what we say, we should do industry relevant, this and that. And then there's another fundamental, I guess, philosophical thing here. What is the job of the university? Is the job of the university to give technology to the industry that they can make into products? Or, my opinion is, my job is here to train younger people so that they know how to solve problems tomorrow. Whatever technology I develop today will be obsolete in 5 years. Right? But if I train the student to think on his or her own, solve problems, figure out problems, I think that's the biggest thing in a PhD. In a PhD, in my opinion, it's not that you have solved a problem. At the end of the PhD, what you should be able to do is, you should be able to independently solve problems. And you should be able to identify what's a problem. That's a bigger thing. What's a problem to be solved? If I train a student like this, then he or she can do it for the rest of their life. The product that I've developed will be obsolete in 2 years. So personally, if you ask me, the goal of a university is something else. Some may agree with me, some may not, and it's fine. There are different viewpoints, and probably everybody has some valid points and some not valid points. Ideally, if I could train students and at the same time produce technology that is commercialized, that's the win-win situation. But increasingly, I have seen that most of the funding organizations, no matter where you go in the world, they will say, I will give you the money for research only if you show me some connection with the industry of the real world. Not everywhere, but yeah. Hungry. So I hope this was sort of useful. Any feedback for me? This GIAN is a one. I don't think the government of India will ever call me again. But just in case, what do you have? Any suggestions for me? What could I have changed or done differently? And don't be shy. Everybody will pass tomorrow. I'm not going to penalize if you say something. You don't have to hold back. Don't think I'll get offended. That's a cultural thing, right? In India, we're still better. For example, in China, they will never ever say anything to their advisor. They keep quiet. Even if I'm doing completely crazy things, they will keep quiet. My Chinese students will never say anything. But the American guy would be totally opposite. I'll tell on my face that, no, you're wrong. To be honest, that's the way it should be. If I'm wrong, you tell me. It's not an ego issue here. So if you think I could improve in some way, yeah.
So my problem is that you're doing lectures on machine learning and all these things.
Yeah.
But whatever you're taught, you're bringing these basic things, they already know the people.
You already knew it.
And but what is the related to the IoT? How these things will be, the example should be when you are teaching clustering, you should have given an example related to the IoT.
Okay. All right.
And same thing is for deep learning also.
All right. What is the relationship to IoT?
Yes, what is the exact relation? Because we have come here machine learning application to IoT. So we have learned the machine learning application, but what is the relation between this?
Yeah.
There was no integration between them.
Okay.
Because while you are talking about the networking thing, at that time you have talked these are protocols for the IoTs. But when you have discussed the deep learning things, classification, clustering, there was no relation how we can relate to.
Sure. I agree with you. I think in that sense, if I had done the examples with IoT data, it may have been better. So there were two things there. So yeah, you made a valid point. I don't disagree with you on that. So one thing was my lecture 3 was supposed to show you this is where machine learning is applicable to IoT, and hopefully we can make the connection here. And the other thing is when I asked the organizers what I said, keep things basic. So if I had known that most people here already know machine learning, maybe I would have done differently. Yeah, ये सब तो नहीं चाहिए शायद. Anything else? Yeah.
Sir, this workshop was application of machine learning on Internet of Things.
Okay.
Was that title existing, right?
Well, I don't know. Yeah, applications of. So what we probably did was we learned IoT and we learned machine learning separately, sort of, right? And there wasn't the connection between them. Yeah, maybe you're right on that one. That's a valid point.
And regarding your good fact, you are a very good speaker, and we should agree to it.
All right.
And topic content may be organizer events, but your style of delivery and everything was fine.
That's good to know. But you should. Well, I guess I shouldn't just blame the organizer. It's I decided ultimately what the contents are. So if there's a mismatch in the title and the contents, that's primarily my responsibility there. We shouldn't hold the organizers. All right then, thank you very much. I guess I'll see you tomorrow.
Thank you.
We'll call it a day from there.
हो गया ना वो सभी वो सब भी हो गया दोनों का ना वेरीफाई कर हाँ हाँ बात करो हु इज मोनिका मोनिका जैन और मोनिका all the days. Monica, you're talking about.
It could be any subset.
Monica Jain.
Everything here.
No, you're talking about Monica Jain.